Module 26210, Circuit Breakers and Fuses. Section 3.0.0, Sizing and Selecting Fuses. Explain how to size and select fuses. Describe fuse ratings and their significance. Identify and describe various fuse forms, classes, and markings. Explain how fuses are sized and selected. Explain how overcurrent protected devices in a circuit are coordinated. And then, of course, there are performance tasks your instructor wants you to do. A fuse is the simplest device for opening an electric circuit when excessive current flows due to an overload or fault condition. A fusible link, encapsulated in a tube and connected to contact terminals, describes the fundamental elements of the basic fuse. The electrical resistance of the link is so low that its simplicity acts as a conductor. It simply acts as a conductor. Every fuse is intended to be connected in series with each phase conductor so that current flowing through the conductor or any load must also pass through the fuse. The continuous current rating of the fuse in amps establishes the maximum amount of current the fuse will carry without opening. When the circuit current flow exceeds this value, the link in the fuse melts due to the heat and opens the circuit. I was saying this earlier. Fuses are amazing things because they act as a conductor. They offer very little, if any, resistance to the circuit at or below their rated current. When they get to their rating or slightly above it, now the fuse link has to start heating up in a way that will melt that fusible link and open the circuit if an overload is continues. If it maintains that overload condition, it's got to trip. It's got to melt. 3.1.0, Fuse ratings markings. Fuses are manufactured in a wide variety of types, sizes, and voltage ratings for both low voltage, 600 volts and below, actually 1,000 volts and below, and medium voltage, over 1,000 volts. The following sections provide details about the essential ratings. 3.1.1 Voltage rating. Most low voltage power distribution fuses have 250 volt or 600 volt ratings. Other ratings are available are 125 volts and 300 volts. The voltage rating of a fuse must be at least equal to the circuit voltage. It can be higher but never lower. For instance, a 600 volt fuse can be used in a 208 volt circuit. Using the fuse within its voltage rating ensures it can suppress the internal arcing that occurs when it opens or blows. If a fuse is used with a voltage rating lower than the circuit voltage, arc suppression is impaired and the fuse may fail to contain the problem. Amp rating. Every fuse has a specific amperage rating. The type of load and the code requirements must be considered when selecting the ampacity of a fuse. Normally, the amp rating of a fuse should not exceed the current carrying capacity of the circuit conductors. For instance, if a conductor is rated to carry 20 amps, a 20 amp fuse is the largest that should be used in the conductor circuit. However, there are some applications where the amp rating may be greater than the current carrying capacity of the conductor. Motors is one example. You're allowed to overprotect the conductors, the circuit conductors, in order to allow for the starting current of the motor. One example is a motor circuit. A dual element fuse is generally allowed to be rated at 175% of the motor full load amperage, while a non-time delay fuse may be sized up to 300% of the full load amp current. The ampere rating of a fuse and switch combination is usually selected at 125% of the load current. There are exceptions here too, such as when the fuse switch combination is approved for continuous operation. Like circuit breakers, it's important that the chosen fuses be able to sustain the largest potential short circuit and fault currents. The interrupting rating of most branch circuit molded case circuit breakers typically used in residential applications is 10,000 amps. Rating is usually expressed as 10,000 AIC, amps of interrupting current. Larger, more expensive circuit breakers may have a rating of 14,000 amps interrupting capacity or higher. In contrast, most current limiting fuses have an interrupting capacity of 200,000 amps and are often used to protect lower rated circuit breakers. NEC Section 110.9 requires overcurrent protective devices to have an interrupting rating at the nominal circuit voltage equal to or greater than the available fault current. Time delay ratings. The time delay rating of a fuse is established through standard UL tests. All fuses have an inverse time current characteristic. That is, the fuse will open quickly in response to a very high current. For low current overcurrent events, the time delay must first elapse before the fuse opens. Specific types of fuses have specific time delay values. For example, the basic UL requirement for class RK1, RK15, and J fuses marked time delay is that the fuse must be able to accommodate the current equal to 5 times its continuous rating for a period of at least 10 seconds. Note that UL has not developed time delay tests for all fuse classes. Some fuses are designed for use where both a time delay and a current limitation for high-level short circuits are needed. Manufacturer's literature should always be consulted to ensure any time delay feature is appropriate for the operating characteristics of the circuit being protected. I'm not going to read hurricane and flood damage victims. Fuse forms and markings. Fuses for homes and businesses typically come in 3 different forms. Of course, there are also different fuse types and classifications within those 3 forms. Plug fuses. These are some of the oldest fuses, and you're not even allowed to install a new plug fuse panel unless it's type S fuses, and even then you really should talk your customer out of it. You should go with circuit breakers. Plug fuses have been around for many years, but they are very rarely encountered today. They're typically found only in the oldest of buildings. Plug fuses have a threaded base for installation into the panel board or fuse holder. There are 2 standard base designs as shown in Figure 11. The Edison base plug fuse is larger in diameter than the Type S fuse, and the body is metallic since the threaded portion acts as the contact point for the load side of the fuse. The base contact is connected to the line side of the circuit. The thread size and pitch of the Edison base corresponds to the base of a standard medium base incandescent lamp. Literally, you can screw a lamp into a panel into the socket for the Edison base plug fuse. The problem with these is that they are interchangeable. You can take a 30 amp Edison base fuse and put it in a 15 amp circuit. Edison base fuse maximum rating 30 amps. Here's a Type S adapter. You can screw this into an Edison base, and then you have a Type S fuse that goes into that adapter, maximum rating 30 amps, but they're not interchangeable. So this is a highlight. Edison fuses are permitted only as replacements in existing installations. All new work that includes plug fuses, which again is rare today, must use Type S fuses in accordance with NEC Section 240.51b. So that Type S has like 0 to 15 amps, and then 16 to 20 amps, and 21 to 30 amps. There are 3 different standards, and you can't interchange them. You can't take a 30 amp Type S fuse and screw it into a 15 amp circuit. There are 15 classifications of Type S fuses from 0 amps to 30 amps. This is a highlight. Each current rating has a different size base and matching adapter. Once an adapter is screwed into an Edison fuse holder, it locks into place and cannot be removed without being destroyed. As a result, only a Type S fuse with a size matching that of the adapter can be inserted. Both types of plug fuses have a strip of fusible metal inside a small porcelain or glass case. The fusible link is visible through a window in the top of the fuse. If the link is broken and or the window is black or discolored, it means the fuse is blown and must be replaced. 15 amps or less, they have a hexagonal window. If the element is broken and the window is not black, and it indicates an overload occurred. If the window is black and discolored, this usually indicates that a short circuit occurred, resulting in a more substantial arc. There are also time delay plug fuses that permit a short period of overcurrent to pass, supporting typical motor inrush currents. In fact, all Type S fuses are time delay fuses. However, Edison-based fuses may be standard or time delay. Note that plug fuses are non-renewable fuses. That is, once the fusible link has opened the circuit, it cannot be renewed and used again. It must be replaced by a new fuse in the same rating and characteristics. Here are cartridge fuses. This is what they look like. Cartridge fuses are most used fuse type in power systems. They offer a wide range of sizes and ratings. Older cartridge fuses were often renewable. The end caps could be removed and the destroyed fusible link replaced, allowing the body of the fuse to be reused. However, they presented a safety hazard because it was too easy to tamper with them and override the built-in safety features. The production of renewable cartridge fuses has been discontinued as a result, and all cartridge fuses are now disposable once blown. So some of these will even have a window on the side to show you when they've blown. These are blade uh, cartridge fuses, and this one is a rejection fuse, meaning it can be inserted into a rejection clip where the regular straight blade cannot be plugged into that. Single element cartridge fuse is the basic component of the single element fuse is the fusible link. Despite the name, a single element fuse may have more than one fusible link. They are electrically connected to the end blades or ferrules and enclosed in a round cartridge surrounded by an arc quenching filler material. Under normal operations, when the fuse is at or near its amp rating, it simply functions as a conductor. However, if an overcurrent event occurs and persists for more than a short interval, the temperature of the link eventually reaches a level that causes a restricted element, a segment of the link to melt. A gap between the form begins to form and the electric arc occurs across the remaining portion. As the arc causes the link to melt, to continue it burning, the gap becomes progressively larger and the electrical resistance across the gap eventually reaches a level that causes the arc to extinguish. The fuse then effectively stops all current flow through the circuit. Suppression of the arc is also accelerated by the filler material around it. Single element fuses are very quick to respond to overcurrent events. They provide excellent short circuit component protection. However, temporary harmless overloads or surge currents may cause nuisance openings unless the fuses are intentionally oversized. As a result, they're best used in circuits that are not subject to heavy transient surge currents and the temporary overloads that inductive loads such as motors and transformers naturally cause. So here's a dual element cartridge fuse. Unlike single element fuses, dual element fuses can be applied in circuits subject to temporary motor overloads and surge currents. They can provide both high performance short circuit and overload protection. Here's a highlight. It says the dual element fuse contains two distinctive types of elements in series. A fusible link, similar to those used in single element fuses, performs short circuit protection function. The overload link provides protection against low-level overcurrent events or overloads. Here's another highlight that says the overload link will sustain an overload that is 5 times greater than the amp rating of the fuse for a minimum of 10 seconds. The overload section consists of a copper heat absorber and a spring-operated trigger assembly. The heat absorber strip is permanently connected to the first short circuit link and the second short circuit link on the opposite end of the fuse by the S-shaped connector of the trigger assembly. The connector electronically joins the one short circuit current link to the heat absorber in the overload section of the fuse. These elements are joined by a calibrated fusing alloy. Let me see if it shows us a picture. I don't see a picture. All right. Fuse classes and markings. Most fuses are used for the protection of branch circuits and feeders on systems operating at 600 volts or below. Cartridge fuses for this category include the UL classes H, K, G, J, R, T, C, C, and L. There are also many miscellaneous fuse types used for special purposes or for supplemental protection of electrical equipment. All fuses are tested and listed by UL in accordance with established standards of construction and performance. NEC Section 240.60C requires that any cartridge fuses used for branch circuits or feeder protection must be plainly marked either by printing or fuse barrel on the fuse barrel or by attaching a label to the barrel that shows the amperage rating, the voltage rating, the interrupting rating, the current limiting where applicable, and the name or trademark of the manufacturer. Fuse sizes. General guidelines for sizing fuses are reviewed in the following section of most circuits you will encounter. Some specific applications require additional thought. In these cases, the load characteristics and appropriate NEC sections must be considered. Sizing dual element time delay fuses. Main service. All ungrounded service entrance conductors must have an in-series overcurrent device with an amp rating no higher than that of the conductor. Exceptions to this can be found in NEC Section 230.90A, ungrounded conductor. As specified in NEC Section 230.91, the overcurrent device must be part of the service disconnect apparatus or be located next to it. Feeder circuit within a motor load, the fuse size here must be at least 125% of the continuous load plus 100% of the non-continuous load. Feeder circuit with all motor loads. For all motors connected to the same feeder, select the largest branch circuit overcurrent device and add 100% of the full load current of the motors. Note that the NEC does not allow sizing up. You must size down. Feeder circuit with mixed loads, select the largest motor branch circuit fuse and add 100% of the full load current of all other motors. Then add 125% of the continuous non-motor load and 100% of the non-continuous non-motor load to determine the value. Branch circuits with no motor loads, the fuse must be at least 125% of the continuous load and 100% of the non-continuous load. All right. So I'm not going to read all of these, but Class R is rejection. 250 to 600 volts, 1/10 of an amp to 600 amps, interrupting rating of 200,000, root mean square symmetrical, listed as current limiting. This is a Class R rejection fuse. It can only be used in, it can be used in rejection clips where other standard cartridge fuses cannot. Sizing non-time delay fuses. If it's a main service, each ungrounded service entrance conductor must have a short circuit protective device either on the load side of the service entrance switch or as part of the switch. It must be capable of managing currents that exceed its trip setting or melting point up to the available fault current. A fuse rated for continuous service at not more than 3 times the ampacity of the conductor is an acceptable option. Option. A circuit breaker with a trip setting of not more than 6 times the ampacity of the conductors is also an option. Feeder circuits with no motor loads. Fuses sized at least 125% of the continuous load plus 100% of non-continuous loads. Feeder circuits with all motors, select the largest branch circuit overcurrent device, then add 100% of all the full load currents of all the motors in the same feeder. Remember, the NEC does not allow you to size up, only down. Feeder circuits with mixed loads, select the largest motor branch circuit fuse and add 100% of the full load currents of all motors, then add 125% of the continuous non-motor load and 100% of the non-continuous non-motor load. Basically, you want to take 125% of the largest motor and add 100% of all other motors. That's true if you're doing all motors. That's true if you're doing some motors and mixed loads. You want to do 125% of the rated current of the largest motor plus 100% of all other motors. If you're doing mixed loads, you want to do 125% of all of the largest motor load plus 100% of all other motors, then add 125% of the continuous non-motor loads and 100% of the non-continuous non-motor loads. Right. And branch circuits with no motor loads, it's 125% of the continuous and 100% of the non-continuous. Any continuous load, any load for 3 hours or more is continuous and you have to size the overcurrent protection device at 125% of that continuous load. Typical single line schematic diagram showing overcurrent protected devices. So any of these are stabbing devices. Disconnecting means a circuit breaker, an electric meter. These are circuit breakers. Let's work through an example. What is this? Assume there's one 25 horsepower motor on a circuit with the following information. It's a squirrel cage induction AC motor, full voltage starting required. Full load amp is 31.6 amps with a 1.15 service factor. NEMA code letter F. In addition, there are two 30 horsepower motors with the following information. Wound rotor induction AC motors, the nameplate primary current is 36.4 amps. Nameplate secondary current is 65 amps at a 40 degrees Celsius rise. Motors are served by a 460 volt, 3-phase, 60 hertz power supply. The feeder ampacity, the motor overload protection, the branch circuit short circuit current, and fault current protection and feeder protection are determined as follows. All right. So feeder ampacity, the full load current used to determine the ampacity of the conductors for the 25 horsepower motor is 34 amps. That's NEC section 430.6A1 and table 430.250. A full load current of 34 amps times 125% is 42.5 amps per NEC section 430.22. Thus, the full load current value used to determine the ampacity of the primary conductors for each 30 horsepower motor is 40 amps per section 430.6A2 and table 430.250. A full load primary current of 40 amps times 125% is 50 amps. So a full load secondary current of 65 amps times 125% is 81.25 amps. The feeder ampacity will therefore be 40 amps times 125% plus 40 amps plus 34 amps, or 124 amps. So you're taking 125 amps of percent of the largest motor amperage plus 100% of all other motor amperages. So they've got two 40 amp motors, so they use 50 amps plus 40 amps because you only need to do 125% of one of them, plus the 34 amps for the 25 horsepower, 124 amps. So we'll go up to the next higher standard rating, probably go to a 125 amp circuit breaker. Overload, when protected by separate overload devices, a 25 horsepower motor with a full load amp current of 31.6 amps must have an overload protection that cannot exceed 125% of the full load amps, or 39.5 amps. NEC section 430.6A2 and 430.32A1, the overload protection for each of the 30 horsepower motors with a primary current of 36.4 amps must not exceed 45.5 amps. That's 125%. If the overload protection is not sufficient to allow the motor to start due to the inrush current, it can be increased according to NEC section 430.32C. Motors marked thermally protected are considered to have overload protection per NEC section 430.7A13 and 430.32A2. Now to size the branch circuit, short circuit, and fault current. If it's a non-time delay fuse, the branch circuit of the 25 horsepower motor must have short circuit current and fault current protection not exceeding 300%. So 300% times 34 amps is 102 amps for short circuit ground fault per NEC table 430.52C2. The next smallest standard size fuse is 100 amps. The fuse size may be increased to 110 amps per NEC section 430.52C1A and section 240.6. If the Maximum value of short circuit and fault current protection does not allow the motor to start due to the inrush current. The value of the non-time delay fuse can be increased to 400%, or 4 times the full load amps, per NEC section 43052C1B. If a time delay fuse is to be used, review section 430.52C1B2. All right. And then they go on to do the feeder section, and they say that it's going to be 80 amps plus 110 amps. It's 190 amps. Basically, it's a maximum rating of the feeder protective device is based on the sum of the largest branch circuit protective device, in this case, a 110 amp fuse, plus the sum of the full load currents of all other motors. The other motor's full load current sum equals 80 amps. Therefore, the rating total is 80 amps plus that 110 amps. It's 190 amps. The nearest standard fuse that does not exceed this value is 175 amps. Selected per NEC section 430.62A. Although the number is closer to the common 200 amp fuse size, remember that you cannot size up. You have to size down. All right. Let's see what this is talking about. Coordination of overcurrent protective devices. Coordination is that you want the overcurrent protection device that's immediately upstream of the thing that needs protecting, that it trips, that you don't trip the main breaker. You don't want to trip a 1,000 amp main breaker because a 20 amp circuit had a fault current and you didn't coordinate. Coordination is the term assigned to the time current relationship among overcurrent protective devices connected in series. This includes fuses in the main feeder, the sub-feeders, and branch circuits. Safety is the prime consideration in the operation of fuses. However, coordination of their characteristics is also an essential consideration. Every fuse properly selected and rated for its application still does not maximize safety. It might still be possible for a fault in a feeder to open the main service fuse before the feeder fuse downstream opens. A branch circuit fault might open the feeder fuse before the branch circuit device opens. So basically, you want to have the branch circuits at current limiting, half a cycle, and maybe the main circuit breaker for that panel at 2 cycles. And the circuit breaker in the main panel feeding that sub panel might have a delay of 3 cycles, and the main 1,000 amp circuit breaker in that main panel might have a delay of 6 cycles. That way, it allows the fast actuation of the 20 amp circuit breaker protecting the branch circuit to trip before the 1,000 amp circuit breaker in the main panel looks and says that there's a problem and tries to trip. Okay. Selective coordination is a selection of overcurrent devices with time and current characteristics that ensure the clearing of a fault or short circuit by the device nearest the fault on the line side. A fault on a branch circuit is cleared by the branch circuit device. The sub-feeder, feeder, and main service overcurrent devices should not respond. With selective coordination, only the faulted part of the system is taken out of the service to minimize the outage. Every device selectivity coordinated is rated for the maximum fault current to which it can be exposed. Coordination is achieved by studying the time to current relationship curves for the device. The selection is then made so that the device nearest any load is faster than all devices closer to the main supply. Each device going backward toward the service entrance should be faster than the device closer to the supply. The main service fuse must have the longest opening time to allow others downstream to respond first. That's coordination. Overcurrent protection is an essential part of any electrical system. Here are some important precautionary measures. Ensure the switch on the circuit breaker is open before making any inspection or changes to either an overcurrent device or to the circuit it protects. Always observe the proper lockout, tagout procedures. Make certain all components are compatible with each other. When an overcurrent protective device opens a circuit, determine the reason before simply changing the fuse or resetting the circuit breaker. Make sure that adjustable circuit breakers are accurately calibrated. When testing, use the test breaker to trip the device one phase at a time. Never substitute a fuse or circuit breaker that's rated higher than the circuit conductors downstream. Here's section 3.0.0 review. Which of the following is an acceptable combination? This is a hard one. You're going to want to do this with your instructor. But you have to decide which one of these is proper. Okay. Edison-based plug fuses are still used in the construction of new single-family homes. False. We do not use Edison-based. We use Type S. And we rarely, if ever, put fuses at all. Ever. When sizing a non-time delay fuse for a branch circuit with no motor load, the fuse size must be at least, and I'm going to let you look back and decide that. And then the selective coordination is used in complex systems to, we just went over that, so I'll let you decide that. Any questions, discuss it with your instructor. You can write questions in the comment section of the video. I'll try to get back to you as quick as I can. Sometimes I don't realize that there's been a comment until 3 days later. I apologize for that. I'm supposed to get an email telling me that there's been a comment made. Sometimes I don't get those emails. So this concludes module 26.2.10, circuit breakers and fuses. I hope you got something out of it. Like always, please give me a like and subscribe to my channel, and I'll see you on the next video. Thank you. Hey, this is Brian Young. If you liked my video, please give it a thumbs up and consider subscribing. I'll see you on the next video.